All right, this is a day 74 assignment. It's an introductions first assignment in the subject of kinetics, and we did change the due date on this, so it's going to be December the 19th, and that's going to be that's going to be Thursday. So let's get started. The first couple pages are a lot of definitions and explanations to get you introduced to the subject of kinetics. So, what is chemical kinetics? So chemical kinetics is the study of rates, that is how fast rates of reactions, just how fast reactions take place. Also could be viewed as wanting to know how far a reaction has proceeded in a certain amount of time. So in 2 minutes, how far has a reaction proceeded? But it has to do with relating time to a reaction. How fast does a reaction take place? What is the scientific term for the speed with which a process happens? And that is the scientific term for speed is rate or rate of change. Are rates positive, negative, or either? Rates are always positive. So you must sometimes put a negative sign on a rate in order to if there is already a negative sign there, you must put a second one on to make sure that it becomes positive. You have to be sure your rate at the end is positive. We'll see what I'm talking about as far as the negative signs here. All right, what is molarity? So that's a review question going back to solutions and stoichiometry. Molarity is the main measure of concentration that's used in chemistry. And the molarity of molarity is the main measure of the concentration of a solute in a solvent. So molarity is equal to moles of solute per liters of solution. What two rates does kinetics deal with? And it deals with a change in molar concentration per change in unit time. And the way that that's expressed is delta, and A is just some chemical compound. It could be H2O, it could be O2, it could be CO2. The square brackets means concentration of molar concentration. So that means moles per liter. So if it is H2O, it'd be moles of H2O per liter of solution. And delta means the change in. And so it's a change in molarity per change in time. The other rate that kinetics deals with, although it mostly will be using molarity and molar concentration, but it also deals with changes in pressure. So if you're dealing with a gas rather than a solution, it would be change in pressure over change in time. So complete the following sentence. Kinetics deals with the rate of change of blank or blank with respect to a change in blank. And that sentence would read, kinetics deals with the rate of change of molar concentration or pressure with respect to a change in time. All right, and write a rate expression for reactant A and for a product B. So a reactant is always going to decrease in value. So the change in the concentration of A is going to be a negative number because it's decreasing. It's going down. That's what reactants do. You use up reactants on the left side of the chemical equation. You create products on the right side of the chemical equation. So it's a change in the concentration of the reactant per change in time. Since this is a negative number, even though you don't see a negative sign inside of this right here, it is a negative number. And since rate has to be a positive, we're required to put a negative sign out in front. So it makes this entire term a positive number. Now, the expression for the rate of a product is increasing. It's what the chemical reaction is making, and so that's going to be a positive number. So you don't need to put any negative signs out here. So the change in the concentration of B, the product B, is going to be increasing, positive number per change in time. And so that's a rate expression. That's what a rate expression looks like for a reactant and then for a product. 9, since a rate must be positive, why is there a negative sign in front of the expression? Well, that was really just explained. The negative sign, there's a negative sign because delta A, the change in the reactant, is going to be a negative number since it's going down in amount, in quantity. And since the amount of A is decreasing, therefore, in order to make the rate a positive number, you have to put this minus sign out in front of it. Okay, what is, slide this up a little, And what is a particulate diagram? A particulate diagram is a proportional, this right here. Particulate diagram is a proportional representation of the moles in a chemical reaction. So if we have this simple reaction to create water, so 2H2 plus O2 gives you 2H2O, then if you wanted to draw a particulate diagram, you would draw two hydrogen molecules. So H2 is a hydrogen molecule, and two of them would be two hydrogen molecules. O2 is an oxygen molecule, and then on the product side, they've broken up and they've become two H2O. So there's an H2O, there's an H2O. Now I could have drawn 4 hydrogen molecules and 2 oxygen molecules to give 4 water molecules. I could have drawn 200 hydrogen molecules and 100 oxygen molecules to give 200 water molecules. In other words, as long as it's proportional, then it's okay. It doesn't have to be exactly the number that you see here. But that's a particulate diagram. It's just a way to visualize a chemical reaction. Okay, now we're on to the second page. And we see a picture of a particulate diagram right there. So use the diagram on the right and refer to the reactions top or bottom. So in other words, number 1 would be the top reaction, that's this one right here. And number 2 would be the bottom reaction, that's this one down here. So which reaction goes all the way? Well, it's a little hard to see in the reproduction, but you have basically 2 reactants. Okay, little interruption. So let's continue on. So which reaction goes all the way to completion? Well, you can see over here, there are some ovals as a reactant. We can just imagine that that's reactant B. Those are the ovals over here, or on either one of these actually. But let's just say, so A is, this is reactant A up here, and there's 1, 2, 3, 4, 5, 6, 7 circles. And for the ovals, there's 1, 2, 3, 4, 5, 6. So at the beginning, before the reaction's even begun, everything is a reactant. There are no products. After 45 minutes, what this is saying is that everything is turned into these ellipses. These aren't the ovals, these are ellipses. They're a different shape, and on the color picture, they're a different color. So all of this has completely changed into all of this. So everything has gone from reactants to products, 100%. If we look at the one down here, we see that we have circles and ovals again. And over here, we have 1, 2, 3 of the ellipses, but we still have 1, 2, 3, 4 of the ovals and 1, 2, 3, 4 of the circles. So in other words, a lot of the reactants are still left after 45 minutes. So assuming that this reaction is going to go all the way to completion, then it's going much, much slower than this one. This one's already done after 45 minutes. It might have been done after 40 minutes for all we know. But it's done after 45, and this one is still has a lot of reactants left. So this reaction on top is going much faster. First of all, it goes all the way to completion, but it's also going much faster. So the answer to that is the top reaction. All 5 of the reactant circles and ovals, all of the reactant circles and ovals are converted to ellipses in 45 I wrote seconds. I think that's minutes down there, though. I think these are minutes. Okay, next. Write 12. Write a possible chemical equation for the top reaction using a proportional number of moles. Well, let's say that the circles represent A up here in this reaction. So we have 1, 2, 3, 4, 5, 6, 7 of A, so we could say that's 7 moles of A right there. And we have ovals. We have 1, 2, 3, 4, 5, 6 ovals. So we could say that they're B. Just make that up, whichever one you want to be B. That one's B. So the ovals are B. So we have 6 Bs. And at the end of the reaction, we end up with 5 of the products. That would be C. 1, 2, 3, 4, 5. So equals 5C. And actually, it should be an arrow, actually, not an equal sign. So let's change that. So that would be a possible chemical reaction. It could have been 14, 12, and 10. It could be any multiple of these numbers as long as it's proportional to the number that you have up here. So that's one possible reaction for the top, one possible chemical reaction for the top particulate diagram. So 7 circles and 6 ovals convert to 5 ellipses. Okay, let's come down here and it says write a possible chemical equation for the bottom reaction using a proportional number of moles. So let's uncover that one. So if we look up here, we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 circles and 1, 2, 3, 4, 5, 6 ovals. So we start off with 6 and 6. By the time 45 minutes has gone by, we don't know how this reaction is going to go to completion, but what we see is we only have 4 circles and 1, 2, 3, 4 ovals, and then we have 3 of the ellipses. So in other words, we've used up 2 circles and 2 ovals to create 3 ellipses. Think about that. We started off with 6. Now we have 4 circles. We started off with 6 circles, 4 circles. We started off with 6 ovals. We have 4 ovals. So we've used up 2 circles and 2 ovals. And what's appeared? 3 of the ellipses. So a possible chemical reaction would be if D and E are the circles and the ovals, then we took 2D, 2 of the circles, plus 2E, 2 of the ovals, to give us 3F, 3 of the ellipses. So that would be a possible chemical reaction for starting with this and ending with this. So 2 circles and 2 ovals disappeared between the first and the 4th frame, here and here. 3 ellipses appeared in the 4th frame, down there. So that's a possible chemical reaction for that particulate diagram. Okay, let's keep going. Which reaction proceeded faster, assuming both go all the way to completion? Well, I think we said that already. Assuming that both consume all reactants and products and produce all products, the top reaction is complete and is faster. Now, a concept that I'll just introduce you to is it's possible that this reaction is not going to go all the way to produce all products, that it's going to end up staying in this state right here where there's some reactants left and some products made, but not all the products are going to be made the way they are up here. And that's a situation that we call chemical equilibrium. Whereas kinetics deals with how fast a reaction proceeds, chemical equilibrium deals with how far the reaction proceeds. A reaction may not go all the way from all products to all reactants as it does up here. It may only go part of the way and then stop. And that would be its chemical equilibrium. We're not really dealing with that concept right now. We're assuming that this reaction is going to go all the way to completion to all products. And so we're just saying, okay, it hasn't gotten there yet. It's just not as fast as this one is. All right. So the next question here is saying, write a complete rate expression for the following hypothetical equation. So this is simply a coefficient. This is some reactant. It could be CH4, methane. And then this is some number of a coefficient, and this is some other reactant. It could be O2 for oxygen. And then you come over here, and there's a coefficient, and this could be CO2. Just represents any kind of product that could come out of this reaction. And this is a coefficient, and this is some other product. It could be H2O. So that could be a combustion reaction. It's just a hypothetical reaction. Okay, so how do you write the rate expression for that? Just remember the simple rules. You simply flip the coefficient, the small a, the small b, the small c, the small d. You make it 1 over each of those things. And then you put a minus sign in front of the ones that are reactants because they're being used up. They're decreasing in value. So you have to put a minus sign in front of them. Just remember those 2 rules, and this becomes very simple. So this is what it would look like. Negative 1 over A, and then you write the concentration of capital A over delta T, change in concentration over change in time. For this one, it's negative 1 over B, change in concentration of B over change in time. Now we go over to the product side. Notice we're setting all of these equal to each other because we want to find a way that if we know the rate of one of them, we can figure out the rate of another. So we have all of these equalities here that we can simply work between them, and you'll see some examples of that very soon. Anyway, when we go over to the product side, it's 1 over C. There's no negative sign because this is being created. It's actually being produced. It's a positive number. It's increasing. Same with D. So it's 1 over D delta, the product, capital D, over delta time. So that's just generically how you would write a rate expression. So let's write one for an actual chemical reaction. This is propane. This is combustion of propane in a combustion reaction. It's balanced. So what we have is we have a coefficient of 1. So you flip that and you got 1 over 1. You put a negative sign. You really don't have to write the 1 over 1, but you do have to write the negative sign there. And this is the change in concentration of propane over change in time. Now we move over to oxygen. It's negative 1/5. You flip the 5 and you got change in concentration of oxygen over change in time. And now we go over to the product side. Still equal signs between all of them. And it's 1/3. It's a positive number because it's a product. It's being produced. So the concentration of this is increasing. And then equals 1 over 4. Flip that number, and it's the concentration of water per change in time. So these things are really easy to write. Just remember those 2 rules. Flip the coefficient, and if it's a reactant, you put the negative sign in front, and you set all of them equal to each other. Why is this? What's going on here? What it's saying is this. It's saying that in a certain amount of time, let's just say the change in time is 1 minute. Let's just say it's, so all of these things have to happen in 1 minute. This one has to use up 1 mole, use up 5 moles. This one has to create or produce 3 moles. And this one has to create or produce 4 moles. And that all has to happen in 1 minute if that's how long this reaction took. So in other words, the moles of CO2 are being created 3 times faster than the moles of C3H8 are being used up. So if I want to equate those two, I have to just take 1/3 of this number of moles is equal to 1 mole of C3H8. Since it's exactly 1 mole there, this is 3 times as fast. So if I want this term to be equal to this term, I have to divide this term by 3 or multiply it by 1/3. That's the same thing. All right, again, you don't have to understand the whys and wherefores, just understand the process. Flip the coefficient, put a minus sign in front if it's a product. Excuse me, if it's a reactant, okay? Okay, so using this rate expression, we're going to solve 4 numeric problems, A, B, C, and D, on the next page. So what we do is, let's read the question. If the rate of consumption of O2 is, and there it is, delta O2 over delta time equals 4.6 times 10 to the minus 5, and that's molarity per second. That's how you express a rate. How many moles per liter that is per second is being used up. What is the rate of production of CO2? So oxygen is on the reactant side, CO2 is on the product side. And so it wants to know what's the rate of production of this. So we only need to use these 2 terms, the oxygen term, this one right here, and the CO2 term, this one right here. So what we're going to do is we come down here and we take this term, so it's negative 1/5. And since we say this delta O2 over delta T, that is this term right here is equal to this. But remember, this is decreasing. So this is really a negative number. There really should be a negative sign in front of it. So I'm going to add that right there, a negative sign. So that's going to be negative 1/5 times negative 4.6 times 10 to the minus 5. And I'm going to leave off the units of measure just to save some space. We know it's going to be molar per second. And that's going to equal this term for CO2. So it's going to be 1/3. You got to bring the coefficient over. And it is positive since CO2 is increasing. So delta, change in concentration of CO2 over change in time. So at this point, it just becomes a simple algebra problem. If we multiply both sides by 3, three times all of this, and 3 times this is going to cancel. That's why we did it. So now we have this term by itself. We've solved for delta CO2 over delta T. And now we just have to crunch the numbers on this. And the double negative signs are going to cancel out. So it's really 3/5 times 4.6. And that gives us 2.76. We're not worrying about significant figures here. So it's going to be 2.76 times 10 to the negative fifth, and that's molarity per second. That's a rate of change, and that equals this term. So we're going to put this term out in front because that's usually the way you express a final equation or a final solution. So the change, the rate at which CO2 is being produced is positive 2.76 times 10 to the fifth molar per second. So if we look up here, we see we're using up more O2 in a certain amount of time than we are producing CO2. So we started with a 4.6 for the O2 being used up, and we get a smaller number. It's positive, but it's a smaller number because we're only producing 3 moles for every 5 moles that are being used up. So if you were to do the math, this is, we just did the math, this is a 3-to-5 ratio. 2.76 over 4.6 is a 3-to-5 ratio. All right, these are pretty easy to do. So let's go ahead and do the next one. If the rate of consumption of C3H8 is, and there it is, and again, it should have a negative sign in front of it because it is being used up, what is the rate of production of H2O? So over here, we don't have any coefficient, so we're just going to go ahead and say that delta C3H8 concentration over delta T. There's no coefficient there, but it is a negative sign out in front. Okay, we had it up there, negative 1 over 1, and that's going to equal 1/4. So we're over here, we're using this, this rate expression right here, 1/4 delta H2O over delta T, and that's a 4. Okay, so now the math is pretty simple. We're simply going to substitute this number in for this. So it's going to be, I'll try to squeeze it in over here. It's going to be negative, and then it's a negative 8.9, we said, because the amount is decreasing. And this is the negative sign that went out in front. And it's there for the purpose of making sure that the rate is a positive number because it must be. 10 to the minus 3, I'm going to leave off the unit of measure to save some space, equals 1/4, and it's still the concentration of H2O over delta T. Okay, so I'm a little tight on space here. I'm going to multiply both sides by 4. Let me draw a line between this so it's not too confusing. Multiply that by 4, multiply this side over here by 4. This cancels with this. So I have isolated the variable that I'm trying to find, the rate of H2O production. So the negative negative becomes a positive positive. And again, it's not a plus. You're not adding it. It's multiplying it, but it's multiplying a positive number. So now it's 4 times 8.9. And when you do that, you are going to get 35.6, I believe. 35.6 times 10 to the minus 3. So I'm going to go ahead and write the answer over here, that the change in concentration of H2O, this is the rate of change, equals 35.6 times 10 to the minus 3 molar per second. Since I'm running out of room, I'm not going to adjust the decimal, but it really should be 3.56 times 10 to the minus 2. Well, I can write it down here. 3.56 times 10. All I'm doing is adjusting the decimal to the minus 2. And that's molar per second. So there's your final answer. Okay, let's keep doing this. If the rate of production of H2O is 5.5, that's a positive number, times 10 to the minus 4 molar per second. What is the rate at which O2 is consumed? Okay, so again, we go up to the equation up here, and there's the rate expression for O2, and that's what we're trying to find. So we're going to write minus 1/5 change in concentration of O2 over delta T equals, and that's the rate of change of H2O. And there's the expression for H2O, so that equals 1/4 times delta H2O over delta T. And we know that this term right here, delta H2 over delta T, is 5.5 times 10 to the minus 4. So down here, I'm going to write negative 1 over 5 delta O2, which is what we're trying to find, over delta T equals 1 over 4. And now we're going to substitute in the number 5.5 times 10 to the minus 4, like that. Okay, am I off screen? Can you believe that? Okay, so let me say that again. So I simply went and got the terms up here, 1/5, negative 1/5 of O2, right there, and 1/4 of H2O, right there. You put them together, there they are. Okay, we're saying that this term right here, this H2O term, is going to be 5.5 times 10 to the minus 4. There it is right there. The 1/4 stays there, and this term stays the same. So now we're ready to do the math. So we're going to multiply. We got to remember that this is a negative number, so they're going to become positive. Just remember, your final rate is always going to be a positive number. So now we're going to multiply both sides by 5 and by 5. So that's going to basically, these 5s are going to cancel out. And so there you have, that's what we're trying to solve for, the rate of change of O2. So it's going to be 1/4 times 5.5 times 5, or you can just say 5 over 4 times 5.5. Anyway, the math is pretty basic. So I'm going to say 5 divided by 4 times 5.5 equals, and I get 6.9 times 10 to the minus 4, and it's molar per second. So that's the rate of that O2 is being consumed. We know the consumption is it's going down, it's decreasing. Okay, one last one. If the production of CO2 is 9.8, what is the rate of consumption of C3H8? So we come up here again, and we got a negative delta C3H8 delta T equals, and it wanted to know CO2 is 9.8, so CO2 right there is 1/3 delta CO2, change in CO2 concentration per change in time. Again, that's how fast it's going. Sorry, I'm off screen. I'll stay on screen now. So now we just do the math on this. We're looking for this number. We remember that this is a negative number inside of here. The change is a negative number right there. I put it right there. That's going to end up being positive. So all you do is multiply. We go ahead and substitute here. So we have, I'm going to get rid of the negative signs. We know the rate's going to be positive. Equals 1/3. And now we can substitute this number right here for that. And we get I'm just going to round it to 3.3. 3.3 times 10 to the minus 7 molar per second. And that's the rate of consumption of C3H8 over delta T. And I'm off screen again. but there it is. Okay, there you go. So that's your final answer. Okay, so that's enough for rate expressions. Um, they're pretty easy. You just do a few of them and hopefully it's there. Okay, let's move on to number 17, I think it is. I got my pages in the right order. Yeah, 17. Okay, so now this is a rate law question. And it says, consider the reaction A plus B gives you C, which is catalyzed by D. So what that means is when we write the reaction, we put the D up above the arrow. A catalyst is a substance that speeds up a reaction, but that is not consumed by the reaction. It will be there at the end of the reaction. So we don't really put it on either the product side or the reactant side. However, for the purposes of doing kinetics, it is included just as if it were a reactant. In other words, as if it were on this side of the equation. Okay, so and I just define a catalyst here. We define a catalyst. A catalyst is a substance that increases the rate of a reaction but is not consumed by the reaction. Catalysts are placed above the arrow when writing a chemical reaction. Catalysts are treated as reactants in a rate law. The reaction takes place at 700 degrees. The following data is as follows. Okay, so we did one of these in class on Tuesday. So let's see if you remember it. We've got a couple here to do to practice. To write a complete rate law, okay, so the reaction takes place at 700 degrees and the following data were collected. So what you did is you ran a reaction 4 times. What you did was you used different concentrations of the 2 reactants and of the catalyst. We don't care about C. C has nothing to do with this calculation to find out the rate law. Only the reactants and the catalysts do. So write a complete rate law for this reaction at 700 degrees. So a rate law is simply written as the rate equals the rate constant, K, and it's a lowercase k, by the way. That's significant because we're going to be dealing with a K for the rest of the course that's a uppercase, it's a capital K. And then it's times the concentration of A raised to some power X, concentration of B raised to some power Y, and the concentration of the catalyst D raised to some power Z. So that's the general form of the rate equation. So what we need to figure out is what is X, what is Y, what is Z, and what is K, and then we'll have a rate equation. All right, so we're going to do that. What's the significance of the 700 degree centigrade? The significance is that a rate constant K is specific to a particular temperature. If you change the temperature, you're going to change the rate constant K. So the point is the 700 number is not a number we need to use anywhere in this calculation. But what it's saying is that the K is only good at 700 degrees centigrade. It's not good at any other temperature. It would be a different number that we would get. Okay, so I was about to write for a particular temperature. Okay, what is the order? Well, first of all, we got to figure out the rate constant. This takes a little bit of number crunching, so I'm going to do it down at the bottom of the page where I have some more space, and at the same time try to be sure I keep this table on. So what we need to do to find out X is we're first going to calculate the X for, this is for reactant A. So what we need to do is find out how does A change, when A changes, I should say, when A changes, how does the rate change? So how does a change in the concentration of A by itself affect the rate of the reaction, how fast the reaction goes? In order to do that, we need to hold B and D constant so that the only thing changing is A. So what we have to do is find two of these reactions somewhere, any two that will keep B and D constant. So if we look at 1 and 2, we see that B doesn't stay constant. If we look at 2 and 3, we see that B doesn't stay constant. If we look at 3 and 4, we see that B stays constant. However, D doesn't stay constant. So what we have to do is kind of look around, and what we'll notice is, after a second or two, is that if we look at equations 2 and 4, if we look at equations 1 and 3, 1 and 3, we see that B stays constant. It's 0.1 in both equations 1 and 3, and that D stays constant. It's 0.05 in both equations 1 and 3. So we're going to use for equations 1 and 3 to find x. So I'm just going to put over here x because that's what we're trying to find. Okay, we're going to use equations 1 and 3. And we're going to create a ratio. And we're going to create a ratio first of all. So again, we're trying to find A. We're going to create a ratio of one of these reactions over the other. You always want to put the bigger one on top. So we're going to put 3 over 1. So in both cases, we're going to put reaction 3 over 1. So what that's going to give us for the reactants is 0.6 over 0.3. And if you do the math, you got a calculator, that equals 2. Now we're going to do the same thing for the rates. And you got to do it in the same order. You got to do reaction 3 over reaction 1, since that's the order we did it over here. And you see that everything is times 10 to the minus 2. So I'm just going to go with the coefficient here. And that's going to be 3.0. That's reaction 3 over reaction 1 is 1.5. And that also equals 2. So now what you do is you take the reactant concentration 2 and you put an x up above it at the exponent, and then you equate it to this 2, the one from the rate. So it's the reaction number, whatever you got, raised to the power equals the rate number. This is the number we got from the ratio of the rates up here. That's 2. So 2 to the x equals 2, so x equals 1. Okay, now let's go ahead and do it for reactant B. So what we need to do is see how a change in B is going to affect a change in the rate. That means we need to hold A and D constant. So go ahead and find two reactions where both A and D are held constant. So now we're trying to figure out the value of Y. And I think you can see pretty quickly where A and D are constant are equations 1 and 2. Okay, right here, A is held constant between 1 and 2, and D is held constant between 1 and 2. So now we're going to go ahead right here. We're going to use 1 and 2 right here, and we're going to set up a ratio. And this time, I'm going to put 1 on top of 2 because 1 is a bigger number. 0.1 is bigger than 0.05, and I like to deal with numbers that are not decimals if possible. So for the reactants, I have 0.10 over 0.05, and that equals 2. Now for the rates, I have 1.5 over 1.5, and that equals 1. So this is the number off screen. Get on screen here. So this is the number I got for the reactants. I'm going to have to maybe shuffle my camera back and forth here. For the reactant, rather, A, so it's 0.1 over 0.5. It was 1 over 2, reaction 1 over reaction 2. And here it's reaction 1 over reaction 2. It's both are 1.5, so that's 1. So now I set up my equation 2 to the y power equals 1. 2 to what power equals 1? Hopefully that's not too tricky a problem for you. You get back on screen again. 2 to the y power equals 1. So y equals 0. So this is going to be a 0th order reactant, and we'll talk about that in a minute. Now we're going back up above, and we're going to try to find the value of Z. And what two equations? Look at that and figure that out. I'll move the camera here. So now what we're trying to do is find out how a change in D affects the rate. So we need to find two reactions where A and B are held constant. And the two that I see are 1 and 4. So A stays at 0.3 in both cases, and B stays at 0.1 in both cases. So those are the two that we're going to deal with. So we're going to do equations 1 and 4. So now I'm going to come back down here. Okay, so in this case, it doesn't matter which one we put over which, well, I take that back, I'm sorry. 1 and 4. So in this case, we are going to put 4 over 1. So it goes 0.1 and 0.05. So we're going to put 4 over 1. So that's 0.10 over 0.05. And just use your calculator. If you can't do this in your head, that equals 2. So I'm back down here again. So 0.10 over 0.05. Okay, that was this number over this number. And now I'm going to do the rate in line 4. Reaction 4 is 3 over 1.5. So I'm going to come back down here, and I'm going to do 3.0 over 1.5, and that also equals 2. So now I take this number down here, and it's 2 to the z power equals this number right here. The rate ratio number is 2. So z equals 1. Okay? So what we have now is our exponents are these 3. So I'm going to write part of the equation down here. We're not done with it yet. Rate equals K times the concentration of A to the first power, that's what X is. You don't have to write the 1, times the concentration of B to the 0 power. And anything to the 0 power is equal to 1. We'll deal with that in a second. Times the concentration of D to the first power. So if I really wrote that in the appropriate way, it's going to look like this. Rate equals K. Concentration of A, we don't put the first power up there. B to the 0 is 1, so it basically goes away. It's going to be 1 times all of this is just doesn't even show up anymore, times the concentration of D. Be sure you understood this part, why B isn't there anymore. B to the 0 power equals 1. So you're multiplying all this by 1, it's just multiplying it by 1. Okay, it's gone. All right, there you go. So this is what it looks like. Now we have to figure out K. So what do? Very simple. We plug in the values of A and of D for any one of these reactions. We can ignore B because it disappeared here. It's not even a factor. So we're going to pick any reaction you want. So we're going to pick reaction 1. So A is 0.3, D is 0.05. Let me get the camera back up there, sorry. A is 0.3, D is 0.05, and the rate is 1.5 times 10 to the minus 2. So I'm going to do that up here. I'll go back up here. So I have rate, which is 1.5. Again, this is reaction 1 that I'm working with. 1.5 times 10 to the minus 2 equals K times 0.3, that's the concentration of A in reaction 1, times 0.05. And that's the concentration of D in reaction 1. So all we do is divide this by these two numbers, and that'll give us K. So we'll go ahead and do that. 1.5 divided by 0.3 divided by 0.05 gives us 100 times 10 to the minus 2. Okay, so 100 is 10 to the 2 times 10 to the minus 2. If you know how to deal with exponents, it's positive 2 minus 2 is 0. So it's basically, let me write it like that, be sure you're clear on that. 100 is 10 to the second times 10 to the minus second. So how do you deal with those two exponents? You add them. 2 plus negative 2 is 0. So it equals 10 to the 0, which equals 1. So that means our equilibrium constant K, this number, is 1. So it means you don't even have to write it, because if it's 1 times this, you just, you don't write 1 times something. It's not there anymore. So basically, this is the way the final rate law would work. Rate equals K, but that's 1, so we're not going to write it, times the concentration of A to the first power, but we're not going to write the 1 up for the first power, times the concentration of D also to the first power, but we're not going to write that. So there it is. That's our final rate law simplified. Okay, so work through those steps and be sure you understand how we got them. And we'll do about 5 or 6 of these problems in the next couple of days, and hopefully they'll make a lot of sense by then, okay? All right, let's get on to C. What is the order of each of the reactants and the catalyst? So the order of A is the reaction is first order, using the proper phraseology here. First order in A. The reaction is 0th order in B, and the reaction is first order in D. Okay, so that's it. That's the orders of each of the reactants and the catalyst. Okay, what is the order of the overall reaction? Well, it's 1. We come up here. It's 1 plus 1 is 2. So this is a second order reaction. Okay, does the product C play any role in the calculation? No. Products never play a role in kinetics calculations. Now, if you're figuring out a rate expression and you want to know how much of the reactant C is produced when so much of reactant A is used, like we did earlier in this assignment, yeah. But when you're doing a rate law, no, they have nothing to do. Okay, so that takes care of question 17.